Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wondered if the drugs we take really work as well as we think? Or if maybe something else is going on behind the scenes? Well, this new paper dives deep into that, looking at how we can figure out the true effect of things, even when the data seems to tell a confusing story. Today we're talking about how scientists try to find the real cause of things, not just what is happening at the surface. You know, that classic saying, correlation doesn't equal causation. This paper tackles that head-on, showing us how we can use smart methods to get closer to the truth about what causes what, especially when we can't always do perfect experiments. Think about it this way. Imagine we have a new drug meant to help people recover from an illness. We want to know if it actually works. It is the gold standard in science to do a randomized experiment where we randomly give the drug to some people and not others. This way, any differences in recovery are likely due to the drug itself. But what if we can't do that? Maybe it is too expensive. Or maybe it is not ethical to deny people a potentially helpful drug. Or maybe we just have data that was collected without a perfect experiment. That is where the ideas in this paper become super important. The researchers in this paper are introducing us to something called the do calculus, developed by Judea Pearl. It is a way to think about cause and effect when you can't run a perfect experiment. They explain that we often rely on our intuition about how things are connected. For example, we know gender might influence whether someone decides to take a new drug. And the drug might affect recovery, but what if we get confusing results? They give us a really cool example using data that shows something called Simpson's paradox. Imagine we have data on patients, whether they took a new drug, and if they recovered overall, it looks like people who didn't take the drug recovered more often. Does that mean the drug is bad? But then, when they split the data into groups, let's say men and women, they found that within each group, the people who did take the drug recovered more often. This is Simpson's paradox. The trend you see in the whole group disappears, or even reverses when you look at subgroups. It makes you scratch your head and wonder what is really going on. The key here is that the groups matter. If the groups are something like gender, where gender might influence both taking the drug and recovery, then gender is a confounder. It messes with the results. But if the groups are something measured after the drug, like blood pressure after taking the drug, then it might be a mediator, something affected by the drug, and then affecting recovery. The same numbers can lead to totally different conclusions depending on what those groups represent in terms of cause and effect. So, how do we get past this confusion? The do calculus helps us be really clear about our assumptions. We can draw diagrams called Causal Directed Acyclic Graphs, or CDAGs. These diagrams show our best guess about the cause and effect relationships between variables. For our drug example, we draw arrows showing if gender causes drug intake, if drug intake causes recovery, and so on. One diagram might show gender influencing both taking the drug and recovery, a confounder. Another might show the drug influencing blood pressure, which then influences recovery, a mediator. These diagrams are crucial because they make our assumptions explicit. If our assumptions are wrong, our conclusions will be wrong, but at least we know why. The core idea is intervention. In a real experiment, we intervene by forcing a variable to be a certain value, like telling someone to take the drug. The do calculus lets us simulate this intervention using our causal model and the data we have even if it wasn't collected that way. When we do something to a variable, like do drug intake 1, it is like we're breaking all the usual causes that would normally lead to that variable and setting it to a specific value. This simulation allows us to calculate a specific thing, the average causal effect. For our drug, it is the difference in the probability of recovery if we intervene to make everyone take the drug versus if we intervene to make no one take the drug. It's asking, what is the drug's effect if we could truly control it? Now, here is where the magic happens. The paper explains how to actually estimate these causal effects from data that wasn't from a perfect experiment. For the scenario where gender was a confounder, they show how you can use the data to figure out the probability of recovery for men and women taking or not taking the drug, and then combine that with the overall proportion of men and women to get the causal effect. It is like using the data to calculate away the confounding. They also show that in the scenario where blood pressure was a mediator, we don't need to worry about it as much for calculating the direct drug effect. The do calculus rules help us know which variables to pay attention to and which to effectively ignore. Crucially, they show that the numbers we get from these calculations can be different depending on our assumed causal structure. In the gender confounder case, they estimated the drug improved recovery by about 5%. In the blood pressure mediator case, they estimated it worsened recovery by about 5%. This highlights how our assumptions about causality are so important. But those calculations gave us just a single number, a point estimate. How sure are we about that 5% or minus 5%? This is where Bayesian regression modeling comes in, which is the focus of the second half of the paper. Bayesian methods are great because they don't just give you a single answer, they give you a range of possible answers with probabilities, telling you how uncertain you are. Instead of just calculating the probabilities, they use Bayesian regression models to estimate those probabilities and the relationships between them. They explain that we can model probabilities like the chance of being male or the chance of recovering given gender and drug use using logistic regression. They then walk through how to do this in R using a package called BRMs. They set up the data, fit models for gender distribution and for recovery rates based on gender and drug use. By getting samples from the posterior predictive distribution, which is basically a way to represent all the plausible values based on the data and the model, they can then combine these samples to get not just an estimate of the causal effect, but also a measure of uncertainty, like a credible interval. For the gender confounder scenario, they get samples for the causal effect. They show that the estimated causal effect is around 5% improvement, but importantly, the credible interval includes 0. This means that while the best guess is a 5% improvement, we can't be totally sure it is possible the drug has no real effect. Then they do the same for the blood pressure mediator scenario. Here they fit a simpler model just looking at drug use and recovery, and again they get samples for the causal effect. This time, the estimated causal effect is around the 5% decrease in recovery, and again, the credible interval includes 0, meaning we can't be certain the drug is harmful. Looking at the plot of the posterior distributions is really helpful. You can see that in both cases, the distributions are somewhat spread out, and the bold black lines representing the 95% credible intervals cover 0. This tells us that based on this data and these models, we don't have strong enough evidence to say for sure that the drug has a causal effect, either positive or negative. So, what is the big takeaway? This paper shows us how the do calculus and Bayesian regression can be powerful tools for trying to understand cause and effect, especially when perfect experiments are out of reach. It helps us to be clear about our assumptions and to quantify our uncertainty. They emphasize that the quality of our causal conclusions really depends on the quality of our causal diagrams and assumptions. They also touch on limitations. Sometimes causal effects are just impossible to figure out from the data, even with the do calculus, especially if key variables are missing. For example, if we had forgotten to record gender in the first scenario, we wouldn't be able to estimate the drug's causal effect properly. The paper highlights that Bayesian methods are great for quantifying uncertainty, especially in more complex situations where simpler methods like bootstrapping become tricky. It's a solid introduction to using these advanced techniques for real-world causal questions. From my perspective, this research is so important because it gives us a roadmap for how to think critically about data. It is not just about finding patterns, it is about understanding the why behind those patterns. The use of Simpson's paradox is a classic and effective way to demonstrate how easily we can be led astray by raw data, without thinking carefully about the underlying causal structure. The Bayesian approach adds that crucial layer of understanding how confident we can be in our conclusions. What is next? Well, this is just the beginning. More complex causal diagrams, real-world messy data, and dealing with even more missing information are all areas for future exploration. But the framework they've laid out here is a fantastic starting point for anyone who wants to go beyond simple correlations and truly understand cause and effect. Thanks for joining me on RUBIN'S Mind Lab. If you found this interesting, give us a thumbs up, leave a comment with your thoughts, and don't forget to subscribe for more deep dives into the science of the mind and beyond. See you next time.